Alex Lazarian will be telling us about formation of small-scale structure in partially ionized gas, probably.
Yeah, probably, because I changed it.
All right, Alex will be telling us whatever he wants, but he'll only be telling us for 12 minutes. Green light says use 10 minutes, orange light says 12, red light says 12.
Okay.
At 13, I body checked you.
Yeah, I understand.
Alex is colorblind.
Yeah.
The top light is red.
Okay. Wake up. First of all, I would like to thank you for still sitting here, because it's been a long day. But this day was very good for me, because one of my former students, Tim Huang, who is going to give you a talk tomorrow, has got a permanent job. And I think we should thank... Okay, so let me start with a teaser. And teaser is about magnetic fields. The Midwest Magnetic Field Workshop is going to happen. And it's happening, will happen on Friday. And if you can, don't miss the event. And why you should not miss the event? Because these guys will be there. And, you know, and they're actually regular participants of our conference, this Midwest workshop. I started it more than 10 years ago, and initially it was in a classroom with 7 people, but now it's a much bigger event. And to tell you, secret, they are giving first talks. So if you are, I don't know whether Carl will wake up, but if you wake up and you are not leaving before afternoon, you can still come. And again, this is a very bad thing that I'm going to say. I'm not asking you if you are coming for just a couple of their talks to pay the registration fee of $25. You can save, you know, free bargain. Okay, and for another teaser, I will show you something, and will not tell you what it is. Actually, the answer. So this is an analysis of the Orion, the Synchrotron emission, which is done with a DRO 1.4 gigahertz linear polarization. And these different dots correspond to the places where we have dominance of alphenic turbulence versus dominance of fast mode turbulence. And I will not tell you, if you are not coming, which parts are which and what it does mean. Okay, so now I'm going to talk about the actual, my presentation, and as you see, I changed this. And you will understand why I changed this. And because we have two people who are we're celebrating. While Carl is showing his tongue, oh, it is not Carl, sorry, but I don't know, maybe you know, some geniuses like to show their tongue. But you see, the other guy is not showing his tongue, so it's not the rule, it's just a random choice. So I wanted to do justice to them. Because if I were talking about something in one talk, I wanted to cover everything in my talk. And this should be real justice, not like this woman, because she's cheating, she's looking in a bad way. So in this case, how to make this justice? We have Carl, who is dealing with tiny structures, and Dick, who is dealing with the magnetization of cloud. How to give now I have 5 minutes probably left, a talk which would cover all these subjects. And my suggestion is to talk about turbulence, because I claim that both guys in these topics are dealing with the consequences of turbulence. And turbulence is everywhere in this room, and this is in the interstellar media. This is the plot from Armstrong, which we extended with Supernova with WAM data. And it shows a big power law of electron density fluctuation. So I will try to address these questions of Dick, how magnetic field can escape while bipolar diffusion will not allow them escape, and we'll talk briefly how can we create probably structures of hundreds of AU scale, which will have really gas pressure excess significant. So let's start with the issue of the star formation. And this is the citation from the Crutcher. So there is no definitive evidence that we have ambipolar diffusion in molecular clouds. Well, let's consider why we need ambipolar diffusion to start with. And we need this because we have a paradigm. And what is this paradigm? This is a paradigm suggested by this guy, Gans Alphen. And it says that if you have a really good conducting media, your magnetic fields are frozen in. So if you have strong magnetic field, plasma obeys it. If you have weak magnetic fields obey plasma. Well, are they really frozen? My claim that they, turbulence freezes magnetic fields, as with this Austin Powers photograph. So how can it do this? And I'm suggesting that we have fast reconnection, which does the job. How can it do the job? And today I forgot my favorite, strings, which I show. I wanted to run away to my office, but just said, okay. I had a good day with him. I had a bad day. I put my coffee on my pants, and then I forgot my toys. Okay, consider these two flux tubes, which are moving together with the eddies, adjacent eddies. As we move these flux tubes with the eddies, they intersect and they reconnect. And this is the process that Ethan Wishniak and me some time ago suggested. And by this process, we can exchange these flux tubes. And this is happening not only at one scale, it's happening at all scales of the cascade. So in this situation, we have an analog of diffusion. And in this case, we can address the problem that Dick Crutcher was showing to us. He showed to us that unlike we expected, for example, in this low-density media, we essentially don't have expected correlation of magnetic field and density. And we can use the arguments about related to the process which I termed reconnection diffusion. And with this reconnection diffusion process, you can estimate the length at which you have this decoupling. And if you know the length and column density, you can find at what scale gravity should become more important than reconnection diffusion. And from that, you can, for example, get this critical length, which is approximately, okay, it's should be in the next. Approximately the column densities you can obtain, and this is approximately the column densities at which we see in column densities the change of the behavior. There were important numerical simulations. The problem nowadays, if you don't do a numerical simulation, no one believes, okay, you can write all these equations. Who cares? Yeah, so therefore it was very important that there were simulations by Santos Lima, a Brazilian student who took the computational box where initially we have a situation when it was a concentration of both magnetic field and density, and as we introduced turbulence, magnetic field would diffuse as we expect for the light fluid from the gravitational potential, and density would concentrate. There will be a handsome man who is my student who will be giving a talk about that. So I'm not taking his bread. I'm just come on Thursday, and he will tell you everything about reconnection diffusion from the accretion disks. But what I want to tell you is something different. I want to tell you that, okay, you can have these simulations, you can play with them, but how do you know whether this is the truth? Because in reality, we have completely different physical situations in terms of conductivities of our media. Therefore, we need theory. Fortunately, this is not just games of putting something in numerical box and seeing what is the outcome. Because we had the intended numerical simulations. I'm not going to talk about this extensively, but there's a numerical simulation by Grzegorz Kowal, which proved the concept of turbulent reconnection. And these are, for example, our predictions, and these are results of numerical simulations, because in our model, the reconnection depends on intensity of your turbulence. And you increase your intensity, you increase the reconnection rate. So there were other ways to test the concept. One was based on the fact that we proved that the fast reconnection is also equivalent to the Richardson diffusion, and these are some simulations by Andrei Bereznyk, who is around here, and Greg Einck, who shows this reconnection diffusion. Also, there are this connection diffusion, and consequences was shown to be present in solar wind. So very briefly and very fast, what about current sheets? And what is this? So these are These are the structures, and you see that there are this, in low density contrast, we have structures along magnetic field, as we discussed. And let me just go to the final transparencies of my talk and talk about the current sheets. In the current sheets, in partially ionized gas, we are creating them on substantial scales. On these scales, for example, 0.3 parsecs in warm and neutral media. It can be also some fraction of a parsec in cold neutral media. Because we are suppressing kinetic energy, but magnetic fields are still frozen in, and therefore we can have this current sheet of the order of Sweet-Parker. And with this current sheets, we can have a significant increase of the density if you have anti-parallel magnetic field and compress density. This is my conclusions, and in fact, we should also again say happy birthday to both of our celebrities. Thank you.
Thank you. Thank you, Alex. Please.
Thank you, Alex, for this bright view of the future. And
It's future, it's present.
Well, it's future for me, because there is something I keep not understanding. You wrote in red why you said viscosity is important, but resistivity is not. So I would like to understand that. I don't understand the physics of that.
Right. Right. So this is profound physical question, and why we have in partially ionized gas more important for turbulence effects of viscosity or the damping compared to resistivity. Well, resistivity in partially ionized gas, for example, in 10 to the minus 4 ionized neutral media is very similar to the resistivity of fully ionized gas. Well, we just take Speed's book, and there is this. No. Edith. The Coulomb cross sections of interactions of ions is significantly larger than the Coulomb cross sections of interactions between ion and neutral. And therefore, with this 10 to the minus 4 even, we have more collisions with ion-ion. So, in this situation, your dissipation of magnetic field through resistivity is still very, very small. But at the same time, maybe I should be more careful and say not resistivity by damping. But at the same time, we know that there is neutral ion and ion neutral damping, which somehow damps the turbulence. And in this situation, we come to the situation that we stop our cascade at a particular scale, which is determined by the neutral ion collisions. But at this scale, we still have identity of our magnetic field lines, and we are creating the structures. There will be on Friday talk by Xiao Xu on the properties of turbulence in partially ionized gas.
All right, unfortunately, we do have more time for questions, but not time for more answers. So we're going to have to thank Alex. Thank you, Alex. And I think we're